Okay, we're going to get started with your calculations for the lab report for experiment 9, chemical kinetics. We're going to begin with the initial concentration of I3-. You may note I have some data here. I have absorbance at time equals 0, and I also have slope and y-intercept. And I got this information from my Pasco data file with the best fit line as the absorbance changes over time. The first thing, again, is to calculate the initial concentration of I3- using Beer's law. Absorbance equals epsilon Cl. Epsilon here is the molar absorption coefficient, which we're going to estimate at 3,000. You will determine that in your experiment doing Beer's law. The concentration is what we're going to solve for. That's in molarity, and then the length of the beam of light, which is 1 centimeter in our case, and in most cases. So solving for that, we say our concentration is the absorbance, 0.269, divided by epsilon, which is 3,000, and our value of L is 1. So my initial concentration here is 8.97 times 10 to the minus 5 molar. I'm going to fill that in my data table, 8.97 times 10 to the minus 5. And these others are 1.00 times 10 to the minus 4 and 9.6 times 10 to the minus 5, if I were to fill those out. Okay, the next thing I have to figure out is the reaction time. The reaction time is just going to be the negative y-intercept over the slope. For our reaction, essentially what this is saying is this is the time when the absorbance equals 0, which is what we're looking for. Remember, when all of our I3- is gone, our reaction will be complete. So just again, using their information from run A, the time is going to be negative 0.269 divided by negative 6.82 times 10 to the minus 4. And I'm going to get 394 seconds. I can calculate those out for all of the runs. This is 394, 208, and 207. Next, I have to find the rate of the reaction. This is just the concentration over time. Because I'm looking at my I3-, I know how much I had at the beginning, and I know how long it takes for all of it to go away. That will give me my reaction rate. So I'm going to use 8.97 times 10 to the minus 5 molar over 394 seconds. And my rate will be 2.27 times 10 to the minus 7 molar per second. So again, I can fill that in up here, and I can do that calculation for each of these runs. I get 4.81 times 10 to the minus 7 and 4.64 times 10 to the minus 7. Now, what you'll be doing in your experiment is everybody from the class will share their data, and you'll be able to find the class average rate. You're going to do this after you eliminate any outliers using a Q test. So I'm not going to have those numbers now because I just have the one run. So I'll use my data as if it were the class data from this point on. The next thing that we have to do is we're going to try and get the order of the reaction with respect to cyclohexanone and with respect to acid. In order to do this, we need to know the initial concentrations. So for the cyclohexanone for run A, I started with 0.75 milliliters. And we know that the concentration of the stock solution was 0.23 moles per liter. I'm just going to write that as 1,000 milliliters. So that would give me the total number of moles of cyclohexanone. I also know that when I prepare the whole solution at the beginning, it's out of a total volume of 3.25 milliliters, or 0.00325 liters. So this will give me my initial concentration in moles per liter of cyclohexanone, which is 0.0531 molar. That's for run A. For run C, it turns out it's twice as much, 0.106 molar. Now, in order to find the order with respect to cyclohexanone, I'm going to have to use the equation that's given in your background information and also in the pre-lab lecture. I'm going to take the log of a couple of things, so it's a little bit confusing, okay? But essentially, what we need to know is we're comparing runs A and C. And the reason we're comparing them is because in those two runs, the concentration of everything else is the same except for the cyclohexanone, which we doubled. So what we're going to do is find this X, or the order with respect to cyclohexanone. And that's going to be the log of the rate of run A, which is 2.27 times 10 to the minus 7. That's right up here, the log of the rate, minus the log of the rate of run C, which again is up here, 4.64 times 10 to the minus 7, divided by the log of the concentration of cyclohexanone in run A, which is 0.0531 molar, minus the log of the concentration of cyclohexanone in run C, which is 0.106 molar. I plug all that into my calculator, and I end up with 1.03, which is good because we're looking for a number that's close to a whole number, so we're going to say that's about 1. Okay. The next thing, again, I'm calculating the initial concentrations of acid. In order to find this, I'm just going to use my, for run A, I had 0.5 milliliters of acid. I know that it's 1 molar, so there's 1 mole per 1,000 milliliters. And again, my total volume is 3.25 milliliters. And I end up with 0.154 molar in run A. And run B, my concentration is twice as much, 0.308 molar. To find the order with respect to acid, I do a very similar thing, except now I'm going to be using runs A and B. The reason being, between run A and run B, everything is the same, except the acid is doubled in those between those two runs. So I'm going to find Y, the order with respect to acid, by taking the log of the rate of run A, 2.27 times 10 to the minus 7, minus the log of the rate of run B, 4.81 times 10 to the minus 7. I'm going to divide by the log of the concentration of acid in run A, which is 0.154 molar, minus the log of the concentration of acid in run B, which is 0.308 molar. And I end up here with 1.08, which again is good. I'm looking for something that's near a whole number. That's about 1. So I can round that to 1. Moving on to the next page, I have to find the rate constant. To find the rate constant, I'm going to use my data from run A. I know that the rate equals the rate constant times the concentration of cyclohexanone. Now I know that's raised to the first order, because it's first order with respect to cyclohexanone, times the concentration of acid, which is also first order. And it's 0 order in I3 minus, so I'm going to leave the I3 minus off. I can solve this expression, K equals rate divided by the concentration of cyclohexanone to the first power times the concentration of acid to the first power. Plugging in my information from run A, I get 2.27 times 10 to the minus 7, that's my rate. I divide by the concentration of cyclohexanone, 0.0531, raised to the first power, and the concentration of acid, 0.154, also raised to the first power. And I get for K 2.77 times 10 to the minus 5 per molar per second. And the last thing I need to do is write the rate law for the reaction. The rate here equals my rate constant, 2.77 times 10 to the minus 5, times cyclohexanone to the first power, times acid to the first power, times I3 minus to the 0th power. And that is all. Good luck with your report, and I will see you next week. Thanks.